Hey guys, today we are going to finish section 1.3, which was graphs of functions. So take a minute and do this warm-up. You are determining the intervals in which each of these three functions is increasing, decreasing, and constant. So take a minute and hit pause and find what interval graph A, graph B, and graph C, each of them, when they are increasing, decreasing, and constant. If you need to, look back in your notes to check and see what it means to be increasing, decreasing, and constant. Make a note, there are no endpoints at any of these three, so your graph does not stop there. So for example, this graph does not stop at 1, 2. It goes on for forever going up in this direction. So be careful of that when you are making your intervals. The first one was tricky because it does look like it levels off, but it's only leveling off that one specific point. So part A is increasing the entire function. It is not decreasing or constant anywhere. It would need to have 2 points and a horizontal line to be constant. All right, go ahead and try B and C. All right, for part B, your function is increasing, going up from left to right, this section and this section. Remember, your answer is your x value, so from negative infinity up to -1, and also from 1 to positive infinity, so 2 pieces, so we separate it by a union. For decreasing, it would be the section going down here. That's decreasing, and there is no part of the graph that's a horizontal line for part B. In part C, it is increasing at this section here, then it's staying constant here, and then going down. So there's 3 different pieces: increasing, negative infinity up to 0, x value, decreasing from 2, oh, I wrote this wrong. I had these 2 backwards. Decreasing from 2 to infinity, and then constant from 0 to 2. All right, relative minimum and maximums. Take a minute and write down these definitions in their entirety. All right, all of this wording is saying if you were to zoom into a graph such that you see a hill or a valley, then that point that is the maximum or the minimum at a zoomed in window is considered a max or a min. So top of a hill would be a maximum, bottom of a valley would be a minimum. Relative means that for the entire graph, it might not be the maximum value, but next to the set of points on your graph, if you were to zoom in, it looks like the top of the hill, so it's a relative max. Something that is the maximum of your entire graph is called an absolute max. And the smallest value of your graph is an absolute minimum. So looking here, these two are bottoms of valleys. So these two, if you were to zoom in your window here, that point is the minimum, the bottom of a valley on that entire graph. Same thing with this one. This one right now is a minimum if you were to zoom in that window. However, this guy over here is lower than this one, but relative to his friends, relative to the points next to him, he is a minimum of the graph. Same mentality of maximums. Top of a hill, when you zoom in and look right here, that point is the top of the hill. Same thing with this one. If these graphs ended and they had points there, then this guy here would be called the absolute max, meaning he is the max of the entire graph, the highest y value that your graph would ever be. And this one down here, if your graphs ended, in this case this picture didn't have points, so I added points here, this one would be the absolute minimum. Finding max and mins on your calculator, so get your calculators out. I have mine right here. Let's graph this function if this lets me. We'll see if it turns on. Apparently this calculator simulation was not allowing me to type, but I figured it out. All right, so top left here, y equals, type in 3x squared minus 4x minus 2. I have an 83, so I have to do this caret for 2. And then we hit graph. There's the graph of our function. So notice that is a quadratic, and we see a bottom of a valley. So we're going to be looking for the minimum. So we go to second, trace, option 3 is minimum. Your calculator is only as smart as you tell it to be, meaning it will find the minimum y value between two x values. So you need to give it an interval. So if you notice here, it says left bound. So hit enter when you're to the left of it. And then I'm going to move my cursor over until that dotted line goes down the valley and then back up a little bit, because you are telling the graph, all right, find the minimum y value of our graph between these two x values. Doesn't matter exactly what they are as long as you go past the valley. And please work. All right. It always says a guess. I don't know why, so hit enter twice. For mine, I have to hit it like a bunch of times. All right, so minimum 0.6666, really close to 2/3. In this case, you're going to give what the graph had here, so 0.667, because it was 6666, and the y value negative 3.33. The relative minimum happens at this location. So that would be what the relative minimum is. If they say what is the minimum of the graph, you are just talking about the y value. So the minimum of your function is going to be negative 3.33. So this is the relative min. The min of your graph is just the y value. If you need the steps again, it was the second button, trace, option 3, and then you do a left bound, enter, a right bound, enter, and then there's a guess. You just hit enter and it will give you the minimum of that interval. So second, trace, option 3, enter, 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 left and right. So you got to make sure that your cursor is between, or outside, I mean, your minimum value that it will find. All right, sketching piecewise functions. We went over evaluating piecewise functions. So if I said find f of 4, you would look over here and say, all right, is 4 in less than or equal to 1, or is 4 greater than 1? Well, 4 is greater than 1, so I'm going to plug it into the bottom equation. A piecewise function means your function is broken up into pieces. The example we did in class, the jump happened at x is 0. In this case, our pieces are going until x is 1 and then starting back up at x is greater than 1. So always plug in 1 point to the left, 1 point equal to. You still plug in 1 into this bottom one, and it's an open circle because you need it to start at 1, but not including 1, but you need it to be at 1.1. So I'm going to pick some values here for us to evaluate. I should do a different color so we can see it on the graph. Let's say f of 0, f of 1, f of 2. Let's just do f of 4 because I said that out loud. F of 0, 0 is less than 1, so we're plugging into this one. So f of 0, 2 times 0 plus 3, that is going to be 3. That is part of the top line. F of 1, still on the top line here. 2 times 1 plus 3, that is 5. So for this top equation, it's a line, y-intercept of 3 with a slope of 2, and we are graphing up to and including when x is 1. So 0, 3, and 1, 5. That point there is the end point. And this here, sorry, my line is not straight when I'm doing this on my computer here. It goes on for forever down there, and it stops at 1. When f is 2, we jump to this equation, negative 2 plus 4 is 2. When f is 4, negative 4 plus 4 is 0. So I have 2 comma 2 and 4 comma 0. and these are connected and they're going on for forever, but I need to know what's happening in this section when f is a little bit bigger than 1, so I still plug in, I'll plug in a different color. I'm still going to plug in 1 into this equation to find the open circle. So open circle at 1. So plug in 1, you would get negative 1 plus 4 is 3. So there is an open circle at 1 comma 3. And we're going to connect that down to this equation here. So if you wanted a nice, I don't know why this keeps changing colors, but whatever. Here is the exact graph. Does it look similar to mine? Boop. Yep. A little less squiggly, but that is the graph. And we can add in the arrows here. That would be the piecewise function. Notice they have that open circle there at 1. So the biggest thing that people need to remember is putting the open circle at the one where it's not equal to. Even and odd functions have to do with symmetry of your graphs. So please put down this definition of an even function. An even function, if you plug in a value for x and you plug in its opposite, so if you plugged in 2 and negative 2, you get the same output. An example of an even function would be a quadratic centered at the y-axis here. So if I were to plug in 2 and negative 2, you would get the same y value. That is an example of an even function. We're going to do an example of how you solve for them in a minute. Write down the definition of an odd function. When it is symmetric about the origin. What that means, if you were to plug in 3 and get a number and you plug in negative 3, your outputs, your answers will be opposites. So for that one, it looks a little interesting. You would have to flip your graph over and then down. So all of these points are repeating. If you multiply x and y by negatives, those would be in quadrant 3 like that. How do we determine when a function is even or odd? Well, this is it here. Put these down. When you plug in a negative x into your function, if you get the same output as your original, that means it's even. If you get your answer to be opposite of your entire function, that means it would be odd. We can't go off of the degree of function. Not every quadratic is an even function. Only the ones that are symmetric about the y-axis. All right, let's take a look at some examples here. Determine whether these are even, odd, or neither. So the way you do this is you plug in negative x into x and see what your output is. All right, so you input negative x for x, so you do g of negative x, and simplify. So this is really a negative 1 x cubed. A negative number raised to an odd power is still negative, and then negative times a negative x is positive x. We need the cube there. So notice both of these terms got multiplied by a negative 1. So this answer really is negative 1 times x cubed minus x, meaning that this function is odd because it is negative 1 times the entire function down here. Part B, if you were to plug in h of negative x, negative x, the whole thing squared plus 1. A negative raised to an even power is positive, so x squared plus 1. Notice that this is the exact same as the original. So when you plug in a negative x and you get back your original function, that is an even. And I just wrote off up here. I apologize here. This is odd, not off, guys. Whoop. And the last one, f of negative x cubed minus 1. That would be negative x cubed minus 1. Notice this is opposite, but this stayed the same. So it's not negative 1 times the whole thing. So this one is neither. So if it's negative 1 times the whole entire thing, it's odd. If it's the original, it's even. Hopefully this helps. Let me know if you guys have any questions, and I will see you guys next time. Thanks, guys.